Welcome to all. Today we will look into designing of shaft under fluctuating loads. In the previous presentations we have already discussed the shaft or the designing of shafts subjected to constant torque and constant bending moments. In this particular presentation we will look into the designing of shafts under fluctuating loads. In order to design such shafts, the combined shock and fatigue factors must be considered. Combined shock and fatigue factors must be considered for the computation of twisting moment and bending moment. Thus, for a shaft subjected to combined bending and torsion, the equivalent twisting moment TE is equal to given in this equation as a root of Km into M whole square Km into M whole square plus Kt into T whole square, where Km is equal to combined shock and fatigue factor for bending and Kt is equal to combined shock and fatigue factor for torsion. And equivalent bending moment Me is equal to this particular equation half into in bracket Km into M. That means Km means combined shock and fatigue factor for bending into bending moment plus root of Km into M whole square plus Kt into T whole square. Then from the following table we can select Km and Kt. This is the table and table which shows the recommended values for Km and Kt. First one stationary shafts, and for second category for rotating shafts we will have the value of Km in this particular column and Kt in this particular column, and this table is available at Km data book page number 56, table 3.1. Km data book page number 56, table 3.1. And here is the question. Here is the first question. A mild steel shaft transmits 20 kilowatt at 200 rpm. It carries a central load of 900 Newton and is simply supported between the bearings 2.5 meters apart. Determine the size of the shaft if the allowable shear stress is 42 megapascal and the maximum tensile or compressive stress is not to exceed 56 megapascal. What size of the shaft will be required if it is subjected to gradually applied loads? This is the question, and this is the solution. Given as P is equal to 20 kilowatt, that is equal to 20 into 10 raised to 3 watts, N is equal to 200 rpm, given W as 900 Newton, L is equal to 2.5 meter, that is span length is equal to 2.5 meter, then tau is equal to 42 megapascal, that is equal to 42 Newton per mm square. Sigma B allowable bending stress is equal to 56 megapascal, that is equal to 56 Newton per mm square. Here D is equal to diameter of the shaft in mm. We have the power transmitted, that power is equal to 2 pi nt by 60, 2 pi nt by 60. From this equation we can easily calculate the value of torque. T is equal to P into 60 divided by 2 pi n, and then that torque is equal to 955 into 10 raised to 3 Newton mm. The maximum bending moment of a simply supported shaft carrying a central load. This is already discussed in the previous semesters. When we have a simply supported beam and a concentrated load acting at the middle of the shaft, then maximum bending moment is at this particular portion, and that bending moment is equal to WL by 4, that WL by that value is equal to W into L by 4. That's equal to 900 into 2.5 by 4. 900 into 2.5 by 4. That's equal to 562.5 Newton meter. This value. We have a simply supported beam like this, and these are the support reactions, and 900 Newton acting at the middle of the span, and this total span length is equal to 2.5 meter. And by symmetry we can say that Ra is equal to Rb. By symmetry Ra is equal to Rb, that's equal to 900 divided by 2, that's equal to 450 Newton. Then we can draw a cross section like this, and this is equal to xx, and we can take this length as x. Then bending moment at a cross section xx is equal to Rb into x. X varying from this at this point x is equal to 0, and at this point x is equal to 1.25. Then Rb into x, when we consider the anti-clockwise moment as positive, then this will become plus. We can select any convenient sign convention for this particular problem, and that's equal to Rb means 450 into x. Then bending moment at B, if this point is B and this point is equal to A, then bending moment at B is equal to, when x is equal to 0, bending moment at x will become bending moment at B, that's equal to 0. 450 into 0. When x is equal to 1.25 meter, then bending moment at xx is equal to bending moment at C, middle of the span. Bending moment at C, that's equal to 450 into 1.25. And when we consider the another axis which is passing to the left hand side of the point C, and in between this A and C, and we can take this entire distance as x, then bending moment at, we can take this axis as x1, then bending moment at x1 is equal to, once again 450 into x positive, and 900 into this particular distance, then minus 900 into x minus 1.25, then if this particular value of x is equal to, if that value of x is equal to 1.25, if that value of x is equal to 1.25, the value of x is equal to 1.25, then bending moment at x1 will become, if this x is equal to 1.25, the bending moment at x1 will become bending moment at x, C, that's equal to, when we substitute that value 1.25 here, then this particular value will become 0, then 450 into 1.25, that's equal to same value as this one. When that x is equal to 2.5, then this bending moment at x1 will become bending moment at A, that's equal to 450 into 2.5 positive minus 900 into 2.5 minus 1.25. That's equal to 450 into 2.5, 450 into 2.5 minus 900 into 1.25, 1.25. That's equal to 0. That's equal to 0. That means bending moment at A is equal to 0. Bending moment at A is equal to 0. Then this bending moment diagram, we can draw the bending moment diagram as this one. Bending moment at A is equal to, bending moment at B is equal to 0. Then bending moment at C is equal to this one. Bending moment at C is equal to maximum value, and that variation is linear. Then this one is linear variation, and again at bending moment at A is equal to, bending moment at A is equal to 0, then that variation also equal to linear. Then this is the bending moment diagram, and the maximum value of bending moment is at C, and that value is equal to 450 into 1.25. 450 into 1.25 Newton meter. 450 into 1.25 Newton meter. That value is equal to 450 into 1.25 Newton meter. 450 into 1.25. This value is same as that one. 450 into that value, maximum bending moment is equal to 450 into 1.25 Newton meter. That's same as this this value, 900 into 2.5 by 4. That's equal to this one. That's equal to 562.5 into 10 raised to 3 Newton m. We know that the equivalent twisting moment is equal to TE. That's equal to root of m square plus t square. Here already we computed the value of maximum bending moment like this. We can substitute that value here. We have already computed the value of the maximum torque like this. Then we can substitute that value here. Then we can easily calculate the equivalent twisting moment. We also know that the equivalent twisting moment is equal to, we have already derived this equation, pi by 16 into tau into d cube is equal to that equivalent twisting moment. TE is equal to this one. We have already derived this equation. Then we can substitute that value in this particular equation. TE is equal to pi by 16 into tau into d cube. Then we can calculate the value of d. Calculate the value of d, diameter of the shaft, required diameter of the shaft. That d is equal to 51.2 mm. 51.2 mm. This is the first case, size of the shaft. And we know that the equivalent bending moment is equal to m is equal to half into m plus root of m square plus t square. That's equal to half into m plus this value is equal to TE. Then we can calculate the equivalent bending moment ME as 835.25 into 10 raised to 3 Newton m, equivalent bending moment. Then equivalent, we also know that the equivalent bending moment is equal to ME is equal to pi by 32 into sigma b into d cube. We can derive this equation from m by I is equal to sigma b by y. This from this particular equation we will deriving this this particular equation. T ME equivalent bending moment is equal to pi by 32 into sigma b into d cube. Then we can substitute the value of ME from this equation. Then we can calculate the value of d, that d is equal to 53.4 mm. Then by using the equivalent bending moment, we will get d as 53.4 mm. And while we consider the twisting moment, equivalent to twisting moment, we will get that value of D is 51.2. Then we can select it. We can select the larger of two values, that's equal to 53.4, and that's equal to that D is equal to 53.4, or we can take it as 55 mm. That is the diameter of the shaft. Here we can use different types of theories of failure, maximum bending moment theory, or maximum shear stress theory, etc. We can compare either of the theories, and we can finally compute the diameter of the shaft. Then the size of the shaft when subjected to gradually applied load. Here again D is equal to diameter of the shaft, and from the table we have already discussed about that table. Table is at KM data book page number 56 and table number 3.1. From that table we can have Km is equal to 1.5 and Kt is equal to 1 for rotating shafts with gradually applied loads. Okay, we will get that value of Km and Kt from that table. Then we know that the equivalent twisting moment T is equal to this particular value, that is equal to 1274 into 10 raised to 3 Newton mm. We have that value of Km and Kt from the, we have already find out that value from the table. Then we also know that the equivalent twisting moment, is equal to pi by 16 into tau into d cube, and we can calculate the value of d. Then we know that the equivalent bending moment, again same equation, but only the difference is that that bending moment must be multiplied by Km and the twisting moment must be multiplied by Kt. That fatigue factors Km into Km and Kt. Okay, then we can easily calculate the value of Me, and we can equate that Me is equal to pi by 32 into sigma b into d cube. Again, these equations are all available at KM data book page number 51. These equations are available at KM data book page number 51 in any other form. Okay, finally the value of D must be same in all cases. Okay, here by equating these two values we can easily calculate D, and that D is equal to 57.7. Then we can compare, while we comparing these two values of D, we can take the maximum value from these two values, that's equal to 57.7, or we can say that value is equal to 60 mm, value of D is equal to 60 mm. Here we can easily say that the diameter of the shaft is higher, or needed a shaft having higher diameter when subjected to gradually applied load than the constant load. In the case of constant load, we have already calculated that value of D as 55 mm, and for gradually applied load that will become around 60 mm. Okay, that's all about today's class. We will look into further designing procedures in the coming presentations. Thank you. Thank you all.